According to a recently published paper from Copernicus University, everything we observe around us, from the tiniest quantum movements to the cosmic drift of galaxies, might in fact be a direct result of time itself. And not just a single dimension of time, but potentially the outcome of a three-dimensional time. Just as we're beginning to grasp the idea that time is a dimension, this claim is truly breathtaking. Yet, to better understand the topic, we need to clarify what physicists actually mean when they constantly refer to the term dimension. It's not easy to find accessible content about string theory. One reason is that certain models of string theory are resolved in 12 dimensions. But how do you explain 12 dimensions to people and turn that into a video? When physicists talk about dimensions, they mean the parameters that define where and how an object or an event exists, essentially, the set of measures that make something unique and distinguishable from everything else. In everyday life, we're very familiar with three dimensions: up, down, left, right, and forward, backward. We can measure an object along these three directions. However, physics isn't limited to spatial measurements. Time is also considered a dimension because knowing when an event occurs is just as crucial as knowing where it happens. This is why physicists interpret the universe through this abstract yet indispensable framework of four dimensions. Without specifying all four, you can't uniquely define an event through measurement. This is called the arrow of time. The author also highlights a much deeper question, one that shakes the foundations of modern physics. If, during dimensional localization, we treat time as a single linear dimension, and yet find that this is insufficient to truly define a unique event, then doesn't that mean all of the physical theories we've built so far, which rely on a one-dimensional concept of time, could be fundamentally flawed? It's a bold challenge, because if time has more than one dimension, then our equations, models, and assumptions might be missing an essential part of reality. And that changes everything. But does time flow the same way everywhere in the universe? At the macro scale, for instance, near a black hole, the flow of time can behave quite differently. Einstein's theory of relativity tells us that as mass or speed increases, time slows down. So, on the scale of galaxies, time is much more flexible than we're used to. On the other hand, in the quantum world, things become even more complex. The direction of time loses its clarity. In fact, in some events, the cause and effect relationship seems to reverse. To reconcile these fundamentally different perceptions of time, the author of the paper presents a rather radical proposal. In order to truly understand the universe, we may need not just three spatial dimensions, but also three temporal ones. Just as we need three coordinates to define an object's position in space, we might also need three separate time axes to uniquely define where an event occurs in time. I must say, this is truly an extraordinary perspective. According to the article, these three dimensions of time represent different physical scales. One corresponds to quantum-level instantaneous processes, another to the flow of time as we experience it, and the third to large-scale transformations occurring across cosmic time. In this model, time is not simply a flowing line. It becomes a structure expanding in three different directions. The author claims this model is not purely theoretical, but that it actually reproduces the physical properties of the universe using this system. That makes the work more than a mathematical curiosity. It becomes a theory that can be experimentally tested. In short, the article says this: time may be far more complex than we ever imagined, and possibly three-dimensional. Now, for those viewers who don't wish to watch the entire video, here's the key takeaway. And from this point on, we'll dive into how the author actually builds the model. The author then transforms these time dimensions into a mathematical model. In this model, he examines the behavior of fundamental particles to see whether these time dimensions function coherently. To make it more tangible, let's use an analogy. Imagine you're painting a picture. The canvas you paint on represents these three time dimensions. In other words, the author proposes that time is the foundational canvas of everything. The paints you apply on this canvas are the particles of the universe: electrons, quarks, and neutrinos. Using this time canvas, the author tries to calculate the masses of particles, because a particle's mass is directly connected to time and energy. But what does that mean exactly? Let's break it down. Einstein's famous equation, E equals mc squared, tells us that mass and energy are simply two sides of the same coin. Energy can come from motion, vibration, or internal structure, and all these processes unfold through time. So, if you know how fast a particle is vibrating in a given dimension of time, you can calculate its energy in that direction. According to the article, a particle's mass emerges from how it vibrates across the three time axes: quantum, classical, and cosmic. Each time dimension resonates with a specific aspect of the particle, and the frequency of that resonance, the rate at which it vibrates, determines the particle's energy. The author sums the energies derived from each time dimension and then applies Einstein's famous equation, energy equals mass times the speed of light squared, to calculate the particle's mass. And here's the most remarkable part. The model developed by the author can calculate the masses of fundamental particles, like the electron, muon, and top quark, with extraordinary precision. The example of the electron is particularly striking. According to the paper, the theoretical electron mass calculated by the model is 0.511 MeV, a value that matches exactly with the experimentally measured 0.511 MeV. This is a powerful indication of how accurately the model works and the significant potential it holds. So how exactly do these three dimensions of time contribute to such precise mass predictions? The author's approach is highly original. He proposes that particles don't just vibrate in space, they also vibrate along the three dimensions of time. Just as a string in space can oscillate up-down, left-right, and back and forth, particles here are thought to vibrate in different modes along three temporal axes: T, representing quantum scale uncertainty; T2, representing our lived, classical time; and T3, representing processes on a cosmic time scale. Each vibration mode contributes to the particle's energy and thus to its mass. But these contributions are not simply added up. They interact in a combined form of resonance. We can illustrate this with a simple analogy. The sound produced by a violin string is not determined solely by the note you press or the thickness of the string. It arises from the complex interaction of multiple simultaneous factors. The time dimensions in this paper work in exactly the same way. One more point is worth emphasizing. In recent years, many studies have strengthened the idea that time is not merely a matter of intuition, but an active component of physical structure. And this model doesn't remain a philosophical curiosity. It produces results consistent with experimental data, making it a serious scientific candidate. In the conclusion of the article, the author suggests that this approach could illuminate not only particle physics, but also cosmological phenomena like the expansion of the universe, quantum fields, and even gravity itself. For this reason, the model may be a promising candidate in the effort to unify the laws of physics. Here's the essence. The concept of time, which we've so far interpreted through intuition, might actually be the key to all physical reality. That's where the importance of this paper lies, because it opens up a brand new window into one of the greatest problems in physics, the unification of quantum mechanics and general relativity. And it does so not through complex mathematical equations, but by showing how everything in the universe falls into place when we think of time as having three dimensions. The model's ability to explain a wide range of physical phenomena, from particle masses to the expansion of the universe, places it far beyond a speculative idea. It becomes a serious theoretical contender. But perhaps the most striking claim is this. This work suggests that time is not just a linear, forward-moving line, but a multidimensional, structural component that reshapes our understanding of reality itself. And maybe the boldest statement is this. If space is merely a painted layer on top of three-dimensional time, then the true fundamental fabric of the universe may not be space-time, but time. That idea is powerful enough to shake the foundations of modern physics. Even more, if this theory is confirmed, it could offer an unexpected path forward for string theory, a framework that has struggled to find experimental support for decades. It might reignite interest among theoretical physicists who have recently moved away from string theory. Why? Because the three-dimensional nature of time could provide a meaningful foundation for the higher-dimensional spaces required by string theory. So, science lovers, today we brought you a truly mind-expanding paper. If you enjoy and share our videos, we can reach even more people who are curious about science. And don't forget to hit the join button. It really helps us keep going. See you in our next video.